Okay, let's talk about challenge one, representation. If we remember, representation is learning to exploit the cross-modal interaction between individual elements across different modalities. And there were three sub-challenges: fusion, coordination, and fission. And we will focus first on the fusion. Fusion is learning a joint representation that model those cross-modal interactions. And so when we study cross-modal interaction, and specifically their fusion, you can see it almost as a spectrum going from basic fusion, where although it is from two different modalities, the representation may be a lot more homogeneous. Maybe they already a vector representation for both modality, while eventually you want to go towards the more complex approach where there the input is heterogeneous, really closer maybe from raw modalities. And although the hard problem is complex fusion, and that's where we want to eventually go, basic fusion is where there's a lot of very important theory, and that's where we'll spend a little bit more time at the beginning. And also, because these complex fusion, when you have two different modalities, can in fact, and it has been a lot of time, move back towards basic fusion, because what people will do is take two different modalities, these raw modalities, bring them into an encoder, into a representations that are a lot closer, and then do the fusion. And that, in fact, brings you back to basic fusion, in fact. So, for example, images, you may have a CNN or a visual transformer, or you may have BERT transformer or some GPT. And so, or just word encoding. So these, just to show that a lot of the theory we'll talk about, basic fusion theory that we'll talk about, is applicable to many cases, even in those complex situations. But there are also approaches that will clearly go beyond the unimodal encoder approach. And as a reminder, the unimodal encoder can be both learned pre-trained or learned jointly with the fusion itself. So let's study the basic concept, the interesting ideas behind representation fusion. And as you remember, this is the goal of learning cross-modal interaction. And I think it is helpful to start simple first before making it even more harder. And so let's start with a univariate case, one dimension for each modalities. Why do I do that? Why are you doing this? Because once you do this, then you can start writing things in the same way you will do in a statistical model, like a linear regression model, where here you will have your constant that doesn't change. You'll have the error, everything that is not modeled properly by your linear regression model, and then you'll have two type of terms, the additive terms, where each modality is modified as a parameter associated with it, so it's weighted, but then simply added, so additive terms, and then you have the multiplicative terms. And so here you could have a simplification of linear regression where it's only additive interactions, and we will often call this sometime even like additive fusion. And then you'll have the multiplicative interaction, or you'll have both of them together. And so when two modalities are to be fused, first question to ask is, is additive sufficient? And in that case, it may be the simplest of them, or should I go more complex to multiplicative, or and there's other non-additive approaches we'll look at. So if we get back to the multivariate case, so it's not just one dimension, but multivariate or multiple dimension for each modalities, then the simplest fusion you could imagine is additive fusion. And that was used early on, and still one that you should take into consideration as a valid baseline model. So there, your modalities are simply added, and your model will learn a way of weighting each modalities. It could be a simple linear way of weighting them, or you could imagine the same thing we have here in the nonlinear case, so where each modality goes through an encoder, gets the modality, and then eventually these are simply added. So that's the additive fusion with more these nonlinearity encoder for each modality. So, in fact, additive fusion could almost be seen as an ensemble or late fusion, because you're bringing each modality as close as you can in that space where the additive fusion will happen. Now, if your modalities may interact with each other and these interaction terms are important beyond additive, then that's where you will start looking at multiplicative fusion. And in the case of univariate, you simply multiply them. That will be one way to do that. But in our case, because you have multivariate, you don't want to just multiply and get only one vector as output. That doesn't model all the different ways the two vectors can interact. Instead, what we'll do is a bilinear fusion. So one vector will be transposed, and then the product in between will give you this matrix. You could call it a tensor, but a matrix that is going to be all the different ways the modality A can interact with modality B. So this is bilinear fusion. And then it eventually got extended this idea, because bilinear fusion, what does it model is the multiplicative terms, but it doesn't have the additive anymore, and that's where the what's called tensor fusion goes a little bit beyond that. It says, hey, let's just add one to each of my vector, and if I do the same trick as the bilinear, now what I will get is unimodal and bimodal together. You get both the unimodal and in a sense, the additive and the multiplicative interaction all in the same tensor. In fact, you can do this with three modalities as well. The figure gets a little bit more exciting, but the tensor, and that's where the tensor fusion is called, is that it creates a tensor, this large matrix, 3D matrix in this case, which has both, which has unimodal, the bimodal multiplicative, and the trimodal multiplicative. But the weight of that matrix can get a little bit hairy, because you can imagine this is just the interaction terms, and then there will be a weight matrix times this, and that can be quite large. So to solve this and to help with that, there was this idea of low rank fusion. So I'm going to show it here with only two modalities, because three gets a little bit harder. But you have your two modalities, you multiply them, and you get your vector, your bilinear tensor Z. And there, this is going to be multiplied by W to get the fusion, the fusion of all the modality through all the possible interaction between them. But you would like to do this in a way that you don't have to create this big matrix. And now you see a matrix is 3D, because there's many different ways, maybe multiple weights for each of these interactions. If you do that and you do it in three modalities, that gets even bigger. So the goal of the low rank fusion will be to simplify this, and simplify three ways. First, to decompose the weights, and to decompose the input tensor, and finally rearrange them in a way that it becomes linear with the number of modalities, and not just that big one. And let's show this visually. I have to thank one of my previous students to do this beautiful animation. But what does it mean by decomposing is that weight vector will be in fact decomposed by these two factors. You can see back to the factors that if multiplied together gives you back the original matrix, but now you have those two factors. If there were three modalities, there will be three factors. And then you do the same for the vector Z, the same way. In fact, it's easy because it's just not multiplying again. That gives you the original factors. And then you rearrange them. And then you simply nicely rearrange them. And that allows you to have a lot more efficient way to, at the end, be equivalent to the tensor, but in a low rank way. So that's the idea behind the Tensor Fusion. And just to recap, what we did is that we had the additive fusion, you had the multiplicative. The multiplicative gave you, in fact, the Tensor Fusion. And for this is for 2 modality, and then eventually for 3. But the way maybe your modalities are interacting may go beyond just linear interaction, and there may be other higher order interaction happening. And due to this, it's good to remember polynomial representation. So in fact, this additive is a first order polynomial, and when you add the interaction term, the multiplicative interaction term, that is in fact second order polynomial, because now there is a second term, second order terms. But does all possible interactions are there, all second order? No, because if you really were to take both of them and really multiply all possible ways, the x squared will also be there. Like so, x8 itself will be another type of second order. Why they interact that? Because eventually we're going to in fact go and start having polynomial beyond 2 orders. So the trimodal, the one that came with the Tensor Fusion, we had the unimodal term, so that's a summation. And then you had the bimodal term that were also sum, and you had the trimodal term. This is a third order polynomial, but again, some of the terms were missing in it to really make it fully what we will call a third order polynomial. And then you can now go and say, I have 2 modalities, and the way they interact with each other are maybe 5 order polynomial. And what you will do is just concatenate your 2 vectors, as we've done, and then multiply them as the number of order you would like. And then with the same low rank approximation we talked earlier, you will eventually get your representation. So that is called high order polynomial. I want to also share another one which is closer to these transformer and self-attention approach, which is called gated fusion. Gated fusion says that you have one modality, you are going to find through a gate, you call it an attention module, you will find a way to learn the best attention weight, and similarly for each modality, and then multiplying this attention with the original value will, and then maybe after that you need to fuse them, so you kind of got both of them and multiply, and now you have attended, you could say attended vectors, and then you can do the fusion. The fusion could be just additive or any of the one we started earlier. So then the question is, how do you design that gate that decides like how much of the A modality should get in, how much of the B modality should be in the fusion? And it can be a linear, and so you could maybe compare A and B and just look at them linearly, or non-linearly, or in fact any kind of kernel function, because what it is, if you have 2 modalities, is you have those 2 modalities, and then you can simply see how similar, because the kernel is really there as a similarity function. And then finally, you get the nonlinear fusion. This is the very popular but somewhat very hard to interpret approach, which says, let me have a network that will simply learn the fusion and give me maybe even a second network, or sometimes it's the same network that does both the fusion and the prediction. So nonlinear fusion is very popular. It could be a multi-layer perceptron or any kind of other nonlinear model you have. But you have to think, when you do those nonlinear fusion, this is a little bit like an early fusion in a sense, because you're just concatenated both, and then you're putting them into a model. This is early fusion. This is back 20, 30 years ago, the approach, but now we're using slightly different ways of doing the fusion. But when you do it that way, in somewhat less explicit way of doing fusion, then you have to ask yourself, what is really happening in my model? Like, is it really learning the non-linearities that I was hoping, these non-additive? So for this, I'm gonna, in fact, start talking now about an approach which we will put into the quantification challenge, challenge number 6. But I will talk about it just because it is very relevant at this point, which is if I have this nonlinear model, I concatenate, I bring in a prediction, I would like to be able to find out, is this really learning the non-additive way or nonlinear way these are interacting with each other? Or can it be just summarized by an additive fusion, like an ensemble of these? Is there a projection? Is there a way for me to project this model into an additive one? And if I do this, do I get the same performance? And if I do, then maybe that means that I didn't model as much of the additive as I wished to. So projection from nonlinear to the additive is this nice landmark paper from EMNLP, who introduced the EMAP method. I will just summarize quickly. The idea is that you will learn the expectation terms. Here you have the expectation. So you have your nonlinear fusion model. It's already learned, already trained. And now you're going to evaluate it. And you're going to evaluate it for all possible value of xb. And you can see the computation complexity of that. But you want it, and you that way, by running it through all possible value of xb, and summing or averaging, then you get that the value of your fusion. If I was only going to do the fusion on A, because I integrated on B, I get only my modality A. What is the prediction from modality A? And similarly for modality B, if I integrate over all the A, I get the B, and then I have what is left from integrating from both of them. When I do this, and in fact to do it efficiently, what you will do is in your training set, because this could be almost like a very complex way, this expectation, but it can be approximated by looking at your training set, or you could be a holdout set or your test set. And then you will simply sum over all your samples there that way. And if your data set is too big, you can look at a subset of it. Now, what you get at the end is that prediction. And that prediction is nice because this prediction is the prediction if I do it in an additive way. And then if that way of doing it, like if I predict with an additive way, and if it is always equal to predicting with the full model, then the hypothesis is that that there is no non-additive, like non-multiplicative, or none of them that have been properly modeled. And so that will be, and that was, in fact, the paper was showing that quite a few models, the performance is very close once you've done this projection, which hint at the fact that maybe those big complex models, although they have all these fancy things, at the end it's maybe just an ensemble or an additive of more of multiple nonlinear models, but just simply added together. And we'll discuss more of this in the quantification challenge. The complex fusion is still an open challenge. How do you model from the beginning the heterogeneity? There's been different approaches. I'm just going to hint at one of them. For example, the channel exchange approach will be an example of that, where as you go, you have two representation, you enforce some sparsity in it, and then as you go from channel to channel, you're exchanging the information, and that can be done over multiple layers doing this. But it's still, in the spectrum of complex fusion, still a little bit closer to basic fusion, because you still need originally some representation that is a vector. So a lot of interesting space to explore the complex fusion. The second type of challenge is representation coordination. Learn multimodal contextualized representation that are coordinated through those cross-modal interaction. So in this case, again, when you study it, there will be strong coordination and there will be partial coordination or weaker coordination. Strong coordination means that I'm learning representation for each modality, but the way I'm enforcing them to be, I'm really enforcing them to be very, very close to each other. Maybe even equal will be the extreme version. While partial will start to be a little bit more subtle in their way of coordinating, and we'll give you some example. But the key for many of the approaches, specifically for the strong coordination approaches, is what we call coordination functions. A coordination function is what coordinates the two, wants them to be very similar, for example. So learning your loss function will often be defining related to that coordination function. So in this, for example, here, I have two modalities. I have an encoder for modality A, an encoder for modality B. I'm learning representations, and I want to learn the parameters of both of my encoders in such a way that I want them to be coordinated. And the strongest you could have is cosine similarity. Like you want this, or one of the strongest, not the strongest, but are they being equal, but strong in the sense it's like the two vector, you want them to be as close as possible, those two representations. And for normalized input, if these vectors, the representation were normalized, this would be equivalent to Pearson correlation coefficient, in fact, especially for the univariate case. So this is one example, but this coordination function could be, as we had discussed, when you see those coordination or similarity function, you have to think like kernel. It can, in fact, any of the kernel function that exists could be used. All these examples still bring relatively strong modality. In fact, you can take the correlation example earlier, and you can start making it slightly less coordinated, but still strong in a sense, which is using canonical correlation analysis. In this case, you're learning in such a way that you have not just one way that the two modalities will be coordinated, but you will define many of those canonical ways, spaces you could call, axes where the data can be correlated. So this is canonical correlation analysis. I want to give you an example a little bit beyond that, because this is canonical correlation analysis as used in a typical approach, which will be what it is how many loss terms you have in this. You have one loss term for generated, your autoencoder for X and your autoencoder for Y, and then you have also at the same time your loss term for your coordination. In this case, could be simple. If you want to really have them equal, it will be cosine similarity, or in this case would be canonical correlation analysis. But there's a nice intuition coming from computer vision that says, hey, those different modalities maybe could be seen as different views of the same object, of the same intact space, and really each view are just like a slight deformation from that. And so this intact one is will be a complete not damaged one, and each of these other view could be seen as a degradation. If you look at this, there's this nice work on what's called autoencoder of autoencoder. What it is that each modalities has again an autoencoder. It's a coordinated representation, but you will suppose that there is, for each sample, there is an intact like representation that is not explicitly viewed, but each modality is a degradation from it. You degrade it for the language or degrade it for the text. And so again, the loss, you have the construction loss, and you have the loss of how well the representation, intermediate representation, match this intact representation. So that gives you an example of coordination. The way these days coordination is often implemented is also through a gated coordination, where you have one gate possibly taking both modality in, and then you get this representation for your first modality, and similarly for your other modality. So gated coordination is very popular, and we'll talk a little bit more later. So the attention just gives you how much of the modality B is to be kept in the representation. And we'll talk more about it in the transformer. But there's one direction I'm really excited, and we see also a lot of progress when we look at coordinated representation, and it's the whole area of contrastive learning. Contrastive learning is not going to enforce a coordination function explicitly, at least, or at least its format is going to be different. Here, you're going to say, you will say that you have two modality, and you have some for both. With the two modality, you'll have paired data. And for now, let's suppose we already give you this paired information. So we'll tell you this image is related to this text. And so the goal is to learn two different representations, one for image and one for text, in such a way that those two representations will bring close to each other the positive pairs, but far from each other all the other pairs that you could have in your data. So that's the goal of contrastive learning: brings closer the positive pairs and push away the negative pairs. The simple contrastive loss will be, in fact, just defining these positive pairs and these negative pairs, and having this similarity function in for both of them. As an example, you could use any kind of similarity function, any kernel you would like. So the positive pairs, you want them as close as possible to each other, and the negative pair, you want them as far from each other. In fact, that loss, that which a small little trick of like doing it, training both from language to vision and vision to language. It's the same contrastive loss, but done both ways. If you do that, that was one of the papers that really changed the field and really brought a lot of interesting things. What they did before I show the result is that they learned text and language. Text and language, image and language, learn two embeddings this way through contrastive learning, and then to show if what is the space, are the space really close to each other, are they, can I do in fact arithmetic with it? And so they took a blue car, they embedded it with that space they had learned for visual. They took the word blue, embedded the word red, embedded, and then they took the blue car minus blue plus red, they get a new vector, and there they just look at the closest images in the space of the visual space, and then they get red cars. Isn't that exciting? So suddenly, at least now it's maybe less exciting, but I can tell you that 8 years ago it was a very exciting result, and they had shown it on others aspect, other word as well, and that really brought a lot of exciting work. In fact, Clip, although it was 8 years later, does almost the exact same thing than 8 years ago. Exactly the same. It's just that now we have we go extensively. So you're gonna take your image and your text. We have a little bit more fancier way. It's not like Word2Vec or something. It's a little bit more fancier image and text encoders. And then once you have these, what you do is simply do a matrix of them, because we already have paired information. Then the diagonal will be the pair, the positive pairs, and everything outside will be the negative pairs. And then you can use a newer contrastive loss that's called InfoNC. It has a lot of the same idea behind, where you want the positive pairs to be close to each other, and then because it's divided by the by this other term that will force the negative pairs and the positive pair. But because we expect a lot more negative pairs and positive pair, then the positive pair doesn't have as much influence. And the similarity function can be, again, just a cosine similarity. So the clip gave great result. We'll see it later when we look at translation, all these DALI and other things. But those two embeddings are great now. If you're going to do any task where there is multimodal interaction and it's very descriptive in nature, like language is descriptive of the image, these are really great embeddings to take. And this is a great example of coordinated embeddings. The last one, which is a little bit harder to understand, and I will say it's also because this is not how typical fusion and coordination are happening, but this is one we believe is very valuable in the future as we start creating more approaches. And here it's to learn a new set of representation that reflects all the factors and clustering in your data. And there we're going to also look at it in the spectrum. On one end, we're going to do modality-level fission. What it is that you have modality A, you have modality B, and you're going to look at it in interaction. And what it is that you're going to end up with only 3 representations. One representation that only contains modality B, nothing of their interaction. Another one that's only modality A, but nothing of the interaction. And then the middle one where all of the interactions between that is contained. So that's a simple way of doing fission. The more interesting one will start looking at factors or clusters, kind of look at how the modalities are interacting with each other and try to find if there's multiple facets in how they can react and interact with each other. But we'll focus first on the modality-level fission. So modality-level fission will say, hey, there is one representation that's all the information that's specific, let's say in this case for language, maybe something more about the syntax, the structure, the vocabulary, the morphology. And maybe there will be another representation that's more about the texture. This is more about the depth information, for example. And then finally, where both modality, the interaction term, and they will happen. So how do we learn this language, and how do we learn these disentanglement between representation? One way to do it is learn modalities and then learn 3 encoders from it. One encoder takes only modality A, another encoder takes both modalities together, and then modality B. And you could imagine have a loss term that will say, hey, I want them to be different from each other. But is it enough to really learn this cross-modal interaction, or how much redundancy? So you can always add kind of autoencoder weights, loss to it, sorry. So you bring back the 2 together and generate. Or if you have a discriminative task, you can even add a loss that says, hey, I know that my task is really a multimodal task in nature. This will happen when you have very correspondence or descriptive text, for example, where there's a strong correspondence between the language and the vision, for example. When you have that kind of case, then you can create this kind of loss which has both the no overlap between representation, have a generative and a discriminative, and that's what the learning factorized papers was doing. But personally, when I start looking at these fission approach, I think it's really good to look at it in an information theory perspective. And remember the idea or the concept of entropy. The concept of entropy, if you have a variable, it measures the degree of randomness and uncertainty, how it varies. If you look at it that way, then you can look again at this Venn diagram and say everything in red, including the intersection, is my modality A, and its entropy of how it varies. The circle blue, which also include in this case all of it, including the intersection, that's how the modality B is varying. Now you have this conditional entropy that's really interesting, is the inside of the red, where it's everything of modality A that if you already knew the modality B, like how much more information will you gain from seeing samples over and over from modality A? And again, seeing it the other way, how is the conditional entropy, how much of B you gain after knowing A? And finally, the holy grail is the mutual information. Looking at how is it that, what is it in the middle, what's really mutual to both. You could see it as the distance, measuring the distance, KL divergence, the measure of the joint, knowing that they have the individual to it. What is it in the joint that's different than having both probability distributions separate? So when you start looking at things in this way, in an information theory perspective, then you can even look at it in a self-supervised way, where each modality could be seen as an augmentation of the original data. In our case, we have each modality by itself, but you could imagine eventually also in the self-supervised learning way. So self-supervised learning, you augment, like maybe you have an image and you shuffle things, or you have a word, a sentence, and you mask something, mask certain words, so that's another way of augmenting. And so you have those two views or two modalities, and then your goal is going to be to learn the middle ground, because you created two modalities, you created two different views, but you know that they come from the same place, so you know that the middle is really what you want to maximize, and that's the mutual information that you want to maximize. And in fact, if possible, you want to learn a representation that minimize the conditional entropy, so that you don't want, once you don't want as much of the conditional entropy part, so that you don't want from the each what's unique at each modality. You only want the mutual information. So that's implementation theory gives us a path toward this disentanglement, and that's, I think, really a lot of interesting future work in this direction. So fine grain is now going a step further and saying, how do I automatically discover those internal cluster, or way the information can be factorized? And one approach, I just have time to share one of these, will be, for example, in the case of multi-view clustering in computer vision and other in multimodal, where you're learning to partition your views in different source of diverse, and so factorization will be one. And multi-view clustering is interesting because it brings those like two concepts. Like if you have multi-view, there is the consensus principle, where you have the maximize the consistency across distinct view. That goes with this idea of intact view. And then what is complementary or supplementary or different from this intact view. And one direction in that sense is multi-view subspace clustering, that learn a unified feature representation from all the subspace and bring it all in this unified representation. So this is a summary of these three challenges: the challenge of fusion, of coordination, and of fission, learning to integrate, to coordinate, or even to factorize the information. The next challenge will be alignment.